Hello and welcome to this video. In this video, we'll be discussing a question. In this question, they are asking us to consider an array A that returns a maximum value between ith and jth index. And max is a user-defined function that returns the maximum of two values passed to it. Okay, so the max function will be like we'll take two inputs, and if first input is greater than second, we'll return the first one. Otherwise, we'll just return the second one. All right. So this is the max function. This is how it's defined. And okay, so inside the function, if I is equal to j, so if these two indices are same, then we return the array element at that index. Otherwise, so this is a base condition in the recursion. If I is not equal to j, what we do is we calculate the midpoint and we return the maximum of uh, I to k and k plus 1 to j when k is the midpoint of I and j. So I want you to imagine like we are finding maximum element from the whole array. So from 0, I will be 0 and j will be n minus 1 if n is the size of the array. So, so in that case, this code can be used to find the maximum element in the array. So it's basically dividing the array into two portions and then finding maximum in each individual portions. So if I have an array of size 6, it will first find the maximum in the first three elements, then next three elements, and then among them it will compare and it will print the final output. So let's try doing with an example. So I'll just move this. Let's say I have an array of 6 elements. Sorry. 176513. So these are random elements I've taken, and my starting index is 0, ending index will be 5, right? 0, 1, 2, 3, 4, 5. Okay, and then it gets keeps getting divided into two equal parts. So you can see 0 to 2, because see k will be 0 plus 5 by 2, so 5 by 2, which becomes 2.5. The decimal part is neglected, so this becomes m of a 0 2, m of aik, and m of a k plus 1 and j. By the way, I forgot to mention that I am considering this find max as m. I'm sure you would have noticed anyway. So yeah, m of a 3 and 5. Then this 0 to again further gets divided. So now I will be 0 and j will be 2. So k becomes 1. So this will call max of 0 comma 1, and this will call max of 2 comma 2, because see 0 I is equal to 0, k is equal to 1, and j is equal to 2. So k plus 1, right? In the second function, we are calling k plus 1, comma j. So it becomes 1 plus 1 comma 2, which is 2 comma 2. So that's how this 2 comma 2 came. And in this one also a comma 3 comma 5. Okay, so 3 comma 5, what it will do is k will become I plus j by 2. So 8 by 2, which is 4. So k becomes 4 and I is equal to 3. And so k plus 1 becomes 5 and j is anyway 5. So yeah, this is how these two functions are called. Then m a 0 1. Okay, so 0 1. So when you have I is equal to 0 and j is equal to 1, I is equal to 0 and j is equal to 1, k becomes 0 plus 1 by 2, which is 0.5, which becomes 0. So that's how this m of I comma k becomes 0 comma 0, and k plus 1 comma j becomes 1 comma 1. And here also 3 plus 4 by 2 becomes 7 by 2, which is 3.5. In integer it becomes 3. So we have 3 comma see I is 3, and k also becomes 3, and k plus 1 is 4, and j is 4. So that's how these two. So okay, so now we have written how the recursion works. That's how the function keeps calling itself. So now we have come to the base condition when we have I is equal to j. So in this case, I'll be returning the element at index 1, which is 7. So this returns 7, and this returns 0th index, which is 1. This returns index 3, which is 0, 1, 2, 3, 5. So it is 5, and this returns the next one, which is 1. All right. So now we'll be calling max of. See, what this function is doing is it is it has called these two functions, but what it is actually doing is max of m of a 0 0, comma m of a 1 1. Now this gets translated into max of 1 comma 7, because this one returned me 1 and this returned 7. Oh, I forgot to close this bracket. So this becomes max of 1 comma 7, which will be 7. So this functions return 7. Anyway, you can see that maximum of 0 comma 1, which is a maximum of 1 comma 7. So in these two elements, the maximum element is 7. And of course 2 comma 2 will just return 2 because of the base condition. I mean element at index 2, which is 6. Now this function will compare 7 and 6 and return 7. Actually, I should write like this. This returns 6, and this should be over here. Yeah. Okay. And now 0 comma 2, what it does is it will compare 7 and 6 and return 7. Alright, so left part is done. Now we'll come to the right part. This was returning 5 and 1. Now what this function will do is it will compare 5 and 1 and return the greater one, which is 5. And this will come to the base condition and return the element at fifth index, which is 1. Now the M of A35 compares 5 and 1 and returns 5. Alright, so now this is a final function call. This is the first function call actually. And from this it got divided into all these recursion tree. So this one, what it does, it will compare 7 and 5, and it will finally print out 7. So as you can see that the code is entirely correct. So there is no way to find a counter example for this code. So for proving code to be correct, you can tell that the code is using divide and conquer, DAC, in which we are dividing the given array of size n into equal parts. So we are dividing a array of size n into equal uh, parts and finding the maximum element. Wait, sorry. We are dividing the array into equal parts till we reach the single element, and then we are comparing and returning the maximum element at every trace, every call. Yeah, I might not be able to frame it properly because English is not my first language. But yeah, that's what is happening. We are dividing the array into equal parts, and then we are comparing. Okay, then we are finding the maximum element in all the in every part, and returning the maximum element to the previous uh, call in the stack. Okay. So, yeah, so the code is correct. You can actually show an example also for proving the code to be correct. In case you are not able to frame an English word, it in English, just write a example so that you don't get 0 marks. If you have time, of course. Then you have to derive the worst case time complexity of this algorithm using recursive tree approach of recurrence. Okay. So what is first of all, let's try to write a recurrence relation for this code, which should be t of n is equal to, I'm dividing into two equal parts of half size. So 2t n by 2 plus big of 1. Yep. So this is a recurrence relation for the given code. Because see, all these are the comparing with max and checking base condition. Those are just those operation will take constant time. They are what do I say? The amount of time that they take doesn't depend on the size of the array. So I don't need to worry about them. So that's why I've written big of 1 here. That's not required. You can ignore it. But yeah, see, if you were to use master theorem, then actually we can solve this using master theorem, and then we would need this big of 1 to avoid any confusion. But over here they have specifically mentioned recursive tree. So let me try doing it. So t of n, it divides into t of n by 2, t of n by 2, which further divides into t of n by 4 into t of n, and to other part also t of n by 4, and here also same thing. All right. So, and this will keep going on up to case steps. So, what we are doing is the height of the tree is logarithmic, log n height, because it's getting half at every iteration. So, after case steps, the height should be reduced to 2k if I'm not wrong. Where at n raised to 2k is equal to 1, it becomes n is equal to 2 raised to k, which becomes k is equal to log n. Yeah. So after k steps, the height of the tree will be log n. And at every iteration, I'm using big O of 1. Here also big O of 1. So this will be multiplied, not added. So into, because see, okay, wait, I'll tell that later. So the height is log n, and at every iteration you are using a single constant complexity. So that will also keep getting added for n log n, right? So this will be for n times. So yeah, you can see at every iteration, though the sum of them may becomes n, and the for this will be till n times. So this becomes n obviously because 1 plus 1 plus 1 for n times becomes n. You can check like 1 plus 1 plus 1 for 3 times, it becomes 3. And the height of tree is logarithmic. So you multiply these two, it becomes n log n. And yeah, that's the complexity for a recursive tree. Actually, I have kind of done optimized way of recursive tree. I don't know the actual steps. I think there were 5 or 6 steps to do that. I'm just finding the height of tree and the complexity at every iteration, and I'm just multiplying them. This is not acceptable way to do it in a exam, in your university exams. Okay. So yeah, this is the n log n complexity. We can actually quickly just verify it using master theorem also. So 2t n by 2. So in master theorem, according to this, a is equal to 2, b is equal to 2, um, n raised to k. So k is equal to 0 and p is equal to 0. And we have a is equal to b raised to k and p greater than minus 1. So for this, the time complexity becomes, T of n becomes big O of, oh sorry, theta of, anyway, it doesn't matter actually, theta of n raised to log a base b into log p plus 1 n, which is theta of n, log a base b is log 2 base 2, which is 1. So n raised to 1 is n, and log p plus 1 n. Wait, I think I might have wrote the master theorem wrong. Wait, master theorem. I'll just check it online quickly. Okay, now I wrote it correctly. So yeah, uh, okay, correct only, no. So log p plus 1, so p is 0, so n log n. Yeah, that's the same answer which we got over here, n log n, using recurrence tree and using the master theorem. So yeah, I'd suggest if you use recurrence field substitution method, try solving the question using master theorem also. If they're specifically mentioned and you can't do anything about it, you have to use recurrence tree, right? But if you have time left at the end, just quickly try using master theorem. And yeah, of course, master theorem can be used if the uh, following constraints are met, like a should be greater than equal to 1 and b should be greater than 1, k should be greater than or equal to 0, and p should be a real number. But yeah, one most important part of master theorem that we have learned is an advanced version of master theorem, which is used for dividing functions. So you can see we have n by b. That's why we have the requirement is b greater than 1. The actual older version of master theorem was for decreasing functions. So this is the actual older version of master theorem. We don't have this in our syllabus actually, but this is used to find the recurrence relation of type t n is equal to t n minus 1 plus O of n. So yeah, this is for decreasing function and this is for dividing function. So instead of n by b, we will have n minus b in this case. And I guess this is more than enough for us because it's actually not very easy to like remember this theorem. And they might ask you to write the master theorem, solve using master theorem. And anyway, you need it for your exam, right? So just learn this one. If you have a lot of time left and you have solved multiple papers and you're very confident with the exam that you'll score 100%, then yeah, you can check this n minus 1 theorem also for decreasing functions. It is in this form. Okay. Yeah, that's it. Have a good day, guys. Hey guys, actually, I just realized that I made a blunder while calculating the time complexity. The time complexity that I mentioned in this code is wrong. It is just a linear time complexity. Actually, this happened because I didn't study recurrence tree method, and I kind of related this to a similar problem in which t of n is equal to 2t n by 2 plus O of n. So that answer is n log n. The time complexity for this code is actually just logarithmic complexity of log n. I'll tell you why is that. So first of all, the complexity is log n. So we made mistake in both the recurrence tree method and the master theorem. So I think it would be easier to understand master theorem error, but let's see the recurrency. So this is entirely wrong. At every step, it's just taking linear complexity, right? So we don't have to add them together. It's already being taken care of in this. But see, if at every step, if it was taking linear complexity, which I just told, if it was big of n, then yes, you'll have to consider it n and multiply it with log n. In that case, the complexity will be big of n log n. So in this case, it's just the the complexity at every step is big of 1 and the number of level is log n. So when you multiply them, the answer comes out to be log n. So this is your worst case time complexity for the given code. Alright, now let's see the error which we made in master theorem. I said that A is equal to B raised to K. But see, A is greater than 2 is greater than 2 raised to 0, right? 2 raised to 1 is greater than 2 raised to 0. Also, 2 is greater than 1. 2 raised to 0 is 1, right? So, yeah, this is wrong. So, it should be A greater than B raised to K. And if A is greater than B raised to K, The master theorem tells us that the answer is big of n log a base b. So log 2 base 2, which is this one. So answer is big of n. Now what has happened? Now from this one we are getting logarithmic, and from master theorem we are getting linear answer. See, logically it should be logarithmic answer. Okay, okay. So you are traversing every element, right? So for accessing every element also it will take linear time. 2 Tn by 2 plus big of 1. Theta of n raised to log a base b. So worst case complexity is big of 1, it's not logarithmic. I might have made an error in this master theorem. Not master theorem, the recurrence theorem. Because see, you can't find a maximum element without accessing every element. Logarithmic time would just access half the logarithmic elements, right? If you are accessing all the n elements, that will take n complexity. So logically, the complexity should be higher than or equal to n. Have I even calculated it correctly? A is 2, B is 2, K is 0, P is 0, n raised to K log P, and why is the recurrence, it's logarithmic, right? Why is the recurrence tree not giving linear? Okay, anyway, the answer from that we got from master theorem is linear. Recurrence tree, I don't know what I have done over here. Just don't consider this. It's wrong. We can erase this whole thing. How can I increase? Anyway, just ignore this. This part, it's not correct. Using master theorem, we got linear answer, right? Big of n using master theorem. Yeah, so I don't know recurrence tree. Using master theorem, I showed you it's coming out to be a linear answer. I think I can do it using substitution method also quickly. So the recurrence relation was T of n is equal to 2Tn by 2. So T of n by 2 would be 2Tn by 4, and T of n by 4 would be 2Tn by 8. So yeah, you substitute it for first 3 times. This is a substitution method, and you name it as 1, 2, and 3. Alright, now you substitute 3 in 2. So 3 into 2 will give me T of n by 2 is equal to 2 times 2t n by 8. So this becomes 4. Now you substitute 4 in 1. What was 1? It was the first equation, the recurrence relation. Tn is equal to 2tn by 2. So the Tn becomes, multiply this by 2, that's it. 2t, oh wait, sorry. Then 2t n by 8. Square bracket is curly bracket. So yeah, after this, you can see the pattern, right? How it's going. So after case steps, T of n would be 2 raised to k, because every step you are multiplying it by 2. So after k steps, it becomes 2 raised to k. T of n divided by 2 raised to k. Here also it's increasing by magnitude 2, right? So yeah. Now we take n by 2k is equal to 1 because that's the base condition. T of 1 is equal to 1. So now we have to find the actual complexity for n. So this makes 2k is equal to n. So the time complexity is substituting 2k is equal to n, or n is equal to 2k. This thing becomes n T of 1, which is just n. So yeah, big of n. So using substitution method also we got big of n. Using master theorem also we got big of n. These are the two methods that I prepared for. I haven't seen recurrence yet. I did it like long ago. I think last semester, and using that only I was trying to solve this, which was a very bad approach. You should never uh, try to solve questions without proper revision. So yeah, actually I spent a lot of time studying recurrence tree last time, so I thought I was like overconfident with this. Not a good way for to go. Anyway, so yeah, the time complexity is big of n for this one. Alright guys, have a good day. Bye.